This lecture is a brief review of complex numbers and the complex exponential function. It's important that we know these because we're going to use them a lot when we talk about the theory of single particle reconstruction. Now, why bother with complex numbers? Well, first, the equations are simpler. Complex numbers do a kind of bookkeeping that otherwise would be quite complex. The other thing is that complex numbers are a natural part of the description of Fourier transforms, which we'll be using a lot. And also in structural biology, you're no doubt familiar with the idea of the magnitude and phase of, for example, the structure factor in crystallography. So to start with, we define the imaginary unit number, which we'll call I. I is equal to the square root of -1. It really has no physical meaning, but as I say, it's a very useful bookkeeping device to have imaginary numbers. So a complex number consists of a real part and an imaginary part, where the imaginary part has the factor I in it. And so here are examples of two complex numbers. Now you can do arithmetic and you can define functions on complex numbers. So for example, the arithmetic is pretty easy. You add the real parts and you add the imaginary parts, and that gives you a real and imaginary part of the sum. You can multiply two complex numbers, and so you just keep track of these factors of I, and you'll notice that this term has the factor I squared, which remember is equal to -1. And so when we collect the terms together, we get a real part and an imaginary part, just as you would expect. The real part of a complex number we write this way. This function real is just returns that real value, and the imaginary part of a complex number returns a real value, which is the coefficient in the imaginary part. The absolute value is given as the square root of the sum of the squares of the two coefficients. And then there's this thing called the complex conjugate, which is exactly the same as the original number, but with the sign of the imaginary part flipped. And here's a little homework exercise. You can show that a number times its complex conjugate gives you the absolute value squared. Now there's another way of representing complex numbers, which is to plot them in a plane, in a so-called Argand diagram. So if we say that the horizontal axis represents the real value and the vertical axis the imaginary value of a number, then we can plot the complex number as a point in the plane, such as this. So we know then that we can represent our complex number by its real and imaginary parts, but there's another representation where we make use of the fact that we can define an angle and we can define a length of this line. I'll call it A. It's going to be the magnitude or the amplitude, and so we can describe the number just as well by a magnitude and a phase angle like that. Okay, now let's move on to the exponential function, e to the x. So e is a transcendental number, and you've heard of the exponential function. It describes, for example, the growth of populations in population biology. It describes the decay of something like the velocity of a bullet moving through molasses. It shows up in finance too. So here's an example. You start out with a certain amount of money in the bank, and you want to know how much money you have at some later time t. And if your bank is doing continuous compounding of interest, this is given by an exponential function e to the rt. So for example, r might be an interest rate of 10% per year, and t might be 10 years, and so rt is equal to 1. And so that then says that at a time t being 10 years, the amount of money that you have is going to be 2.718 times your original amount of money. That is, your money doesn't double in 10 years. it increases to 2.7 times the original value. So that's our friend, the exponential function. Another representation of the exponential function is shown here. This is an infinite series that represents the exponential function. And a very important approximation that we're going to be used is the first order approximation in a Taylor series, which says that if x is something very small, then e to the x is very close to 1 plus x. And this approximation we will be using, for example, in the weak phase approximation in electron microscopy. Now, Leonhard Euler looked at this series and noticed that if he made x imaginary, the series then looked like a sum of the series for cosine function and for the sine function. And so he was able to prove that the exponential function of an imaginary number is actually related to these two trigonometric functions. So remember what cosine looks like. Cosine is 1 when the angle is 0, and it repeats with a period of 2 pi, and it's an even function. That is, it's symmetric around 0. The sine function is exactly the same, except that it's an odd function. It is antisymmetric around an angle of 0. And you can get from the cosine to the sine function by making a phase shift of pi over 2, or 90 degrees. Now, if you think about it, we can do a plot of the complex exponential in the same kind of way. So we plot the real and imaginary parts of the complex exponential. When theta is equal to 0, we are sitting here on the real axis at the value 1. And as theta increases, we trace out a circle. Not a very good circle here, but that is a unit circle. And so when theta is pi over 2, we're here. When theta is pi, there. When it's 3 pi over 2, we're there. And so we trace out a path, a circular path on the unit circle. So we can try to plot this function. Well, we start out with exactly what I drew on the board. But if we add a third dimension, which is the theta dimension, and plot here imaginary part vertically, real part horizontally, we see that if we look at this, trace, which is a helix, from the side, looking at the imaginary part, it looks just like a sine function. Starts at 0 there. And then if we rotate our representation, so we're looking at it from underneath so that we just see the real part, there is our cosine function. So based on what we have here, we can be a little bit more sophisticated about our representation as a number in the complex plane. Specifically, we know that if we represent z as an amplitude in a phase, then the amplitude is just the absolute value of z, and the phase is just the inverse tangent of the ratio of imaginary to real parts. And we can say that z is equal to the amplitude times e to the I theta. So here's a formal description of a complex number as in polar coordinates, so to speak, as in magnitude and a phase. So that's it for our review. Here's another exercise. You probably recall how awful it was to learn these trigonometric identities when you took trigonometry. But knowing now about the complex exponential, it's straightforward to prove trig identities like this. And this is an example of how complex numbers and the bookkeeping that automatically happens make equations simpler.